Hello everyone, this is Ning Yang. Today I'm going to present a paper on partial least square optimization, dropping convexity for better efficiency and scalability. This work is joint work with Zhehui Chen, Chris Lee, and Tou Zhao. Okay. So here's the outline of today's talk. So let's starting from the introduction on multi-view representation learning. So nowadays we have access to many multi-view data that's of a same object. For example, we have a speech and text of a same paragraph or book, right? We have a video and audio of the same thing on on TV, or we have a video and text on many things. Okay. More details can be found in these references. However, then the question is as follows. How to know useful features from multi-view data? Even though you have the multi-view data, how will you use them to learn the features? Okay. So a way to do this is this partial least square. So first of all, we turn the data into vector representations. For example, we have a data pair that's from two views, x and y. X from the x-dimensional space, y is from the y-dimensional space, such that dx plus dy equal to d. So then we have this intuition that if both of them are noisy but they are describe the same thing, so the common information is the signal or features, right? Okay. So what do we do to extract the common information? The PLMS method, partial least square method, is by solving the following optimization problem. You need to find the two vectors u and v that maximize UT transpose times this covariance matrix times V, subjected to that U and V are univectors. Okay, you can think like we want to find the subspace to maximize the covariance between the two random variables. You project x into U and project y into V, right? You find the subspace to maximize the covariance of the two random variables. That's the PLMS method. Of course, you can think it as just a singular value decomposition, right? Okay, so you have two views of data x and y. The subspace you find has to maximize this projected random variable. That's actually your signal. Okay. So we are studying in this. So there are also other methods. For example, in Aurora et al. 2012, there are many other methods. For example, CCA, canonical correlation analysis, and many more. We are focusing on SVD in this paper. Okay. Furthermore, we are studying in this data laden or streaming setting. So in this setting, we are observing data of the form x1, y1, x2, y2. You're just observing a pair at a time. Okay. So in this data laden regime, we want to overcome the big data challenge. Okay. Of course, you can treat the stream of data as the data points in your hard drive, and you can use that to do a sample average estimation of the covariance matrix. But that's expensive. Why? Because you need to use space dx times dy, right, to store the entire covariance matrix. Furthermore, the SVD for this matrix in general costs dx times dy squared or dy times dx squared time, or you use power method, and then again you need to access to the entire matrix that has memory dx times dy, and also time complexity is dx times dy. Okay. So in this data laden regime or setting, we want to make a single pass over the data and at the same time output the estimation for the optimal subspace and use space only of the subspace, right? Using the space OD just to store the top two singular vectors. And using nearly optimal number of samples. What I mean here is that we use a number of samples that's comparable to the sample average estimation. Okay. So in this setting, and the goal is this. So what is our result? Our result is as follows. First of all, we give an efficient non-convex streaming optimization algorithm with provable guarantees. Okay. We're using like a OD space and O epsilon to the -1 log epsilon to the -1 samples to obtain an approximate solution. The epsilon describes the error, the subspace angle between the solution and the true solution. Okay. So we give an overall analysis of the algorithm based on ODE and SDE approximation. ODE means ordinary differential equation, SDE means stochastic differential equation. Later on, we demonstrate the global geometry and the dynamics of the non-convex optimization problem. Okay. So what is our algorithm? Our algorithm is as follows. Each initialize a unit vector arbitrarily u0 and v0. Our algorithm updates our current solution by adding a new solution once you get a new sample data sample. This update is as follows. Xk, you use yk inner product with the current v and times xk and minus this number uk or xk, yk, vk, and then times uk to our current sample. Okay, so basically you can think if you look at it closely, basically each time we update our current solution by a new vector times the number, new vector times the number, right? That update can be computed in just OD time. Eta is the learning rate that prefixed it. Okay. So why do we get this weird algorithm? First of all, okay, this algorithm is actually a special case of a generalized Hebbian algorithm. Here's the derivation. So first of all, write down the Lagrangian for this optimization problem. Introduce mu and sigma as multipliers. So KKT condition tells us the optimal multipliers should be u equal to sigma equal to 1/2 times this ut times sigma times this covariance matrix times v. Okay. So based on this, we take a due update. We want to solve this saddle point problem for L. We take the due update as follows. uk equal to sigma k and replace x and y, expectation x and y by xk, yk, right? So our prior update is following the gradient of the Lagrangian. Is just we then plug in this uk and yk into the gradient, and this just gives our algorithm. That's primo free, dual free. Okay. So why this algorithm works? Like it comes up this analysis. First, we use an ODE to approximate our algorithm. So to use the ODE to approximate our algorithm, we consider this continuous time approximation. First of all, we take u eta as this u. We define a new random variable that is a continuous time random variable. The value of this is a vector. That's t divided by eta, and also v is the same, vt divided by eta. Okay. Under mild assumptions, we will show that these two new random variables has very good behaviors. First of all, the first assumption is finite moments. So we require that the sample data x and y, the two normal of sample data x and y has finite first moment and a finite second moment. Okay. Is the first assumption. The second assumption, we require a spectral gap in this sigma in this covariance matrix. We require that the first singular value is strictly greater than the second singular value. Under these two assumptions, we show that these two new random variable weakly converges to the following ordinary differential equation. Okay, as eta goes to 0. So this is the equation. So you see du dt equal to sigma times v. Sigma is the covariance matrix times this number times u, and vice versa for v. The solution for this can be obtained very easily by symmetrization of this matrix of these equations. We obtain the following solution: hi over h1 t equal to some exponential function of lambda I minus lambda 1 times t, while hi is the subspace angle. For example, the current solution inner product with the true solution, ui star and vi star, and left and right singular vectors of this covariance matrix. Okay, so how does this solution tells us? It tells us as follows. Since hi is the subspace angle between the solution to the ith eigenvector, that's not what we need if I is greater than 1. Okay, so it's actually the error. So this thing just shows that it decreases exponentially if h1 initially is not 0. Basically, we can conclude that starting from some point sufficiently far away from any saddle point, let's say h1 is not 0, then it will converge to the global maximum. Our algorithm will converge to the global maximum, right? Okay. So then we have the ODE that characterize the convergence of our algorithm. Then we raise two questions. First of all, how does the algorithm behave once the updates are close enough to the global maximum? The second one, will the algorithm be stuck in the local minimum and the saddle point, right? To answer this question, we need to zoom in the local regions by rescaling the time variable. What I mean by zooming, I define a new random variable, zi. Zi is equal to this subspace angle divided by square root eta. Okay, so if you're starting from some saddle point, let's say uj and vj, and that's not 1 for j greater than 1. So that's the saddle point. When eta goes to 0, the trajectory of z eta converges weakly to the following SDE, stochastic differential equation. dz equal to minus lambda j minus lambda I. So j is the starting point, remember that. So the dt plus this term, beta ij times db. db is the standard Brownian motion, okay? So if you're starting from this saddle point, you get this ODE, okay? And this, of course, it also characterizes when you're starting from j equal to 1, that just tell you how this algorithm behaves around the global maximum, okay? So this equation actually describes this OU process, okay? The solution can be done by simple eta calculus or this Planck-Focal equation. So this is the solution. We have this is a constant term, zi0, plus this is a constant, times this term, this is a fluctuation term, and this is another term, a modulation term, that's what I call. Okay, so let's look at I equal to 1. You're starting from any lambda j. Since if j is smaller than 1, this thing is strictly greater than 0, then this thing grows exponentially. If you look at the variance of this random variable, I mean, this thing is actually, this term is actually a constant variance, but because of this term, this variance exponentially grows. It just tells you that this SDE will amplify the small fluctuation exponentially. And that just tells you it will escape from this saddle point. And of course, in our new version of the paper, we showed that the saddle points, all the saddle points satisfy the strict saddle properties. That is another reason why our algorithm can escape from this saddle points. Okay, and also because of the same equation, we can show that this algorithm updates will fluctuate around the global maximum once it is there. Okay. So here is an experiment, shows exactly how our ODE and SDE describes. We take a toy example of a 3x3 matrix. So our algorithm have 3 phases. In the phase 1, it's starting from some saddle point and fluctuate, and the fluctuation grows exponentially. And then it decreases, the arrow decreases because of the ODE characterization, right? It decreases very quickly to be around the global maximum, and from there it just fluctuates around the global maximum. let's see, we do some comparison with some other solutions for the same problem. For example, we do a comparison between this convex relaxation matrix stochastic gradient descent. Our algorithm is much faster. For example, this blue line is our algorithm, this purple line is the MSG. Okay, this is the iteration complexity, this time complexity, the same. Our algorithm runs much faster. Okay, that concludes the talk. Thank you.